My name is Jack Weast from Intel and Mobileye, and I'm here today to talk to you about metrics, methods, and assumptions, the state of automated vehicle safety assurance. So let us consider what our future with automated vehicles will look like. The original introduction of the automobile was quite chaotic. The automobile had horses, people, pedestrians, food carts, bicyclists, all sorts of crazy things. And so the introduction was very messy. It's unclear who had right of way, what driving safely even meant, in the context of all of these other agents. And so we should consider, do we want this to be our future, or would we prefer something better? So we should ask ourselves, though, what if every automated vehicle that was deployed had a different definition of what it meant to drive safely? What if every state in the US or country in Europe had a different definition of driving safely? What if every time there was an accident, it took years of litigation and lawsuits to ultimately decide which vehicle was driving safely? So these things, if we don't fix them, could result in a very messy introduction for automated vehicles, and we have an opportunity to do better. And so really the key point here is that unless we can come to an agreement on what it means for an automated vehicle to drive safely, there will be no automated vehicles on the road. So why are safety standards necessary, and where do they fit into the whole mix? Before we talk about automated vehicle safety standards, let's look first at a case study. So consider the FAA. In 1997, the FAA created the Commercial Aviation Safety Team, or CAST. And this team was really important for a reason. It was the first time that the FAA looked at proactive identification and mitigation of risk, not just looking at a crash and what happened, but considering what kinds of crashes might happen. And then let's define and prevent those in advance to a level of acceptable risk to society. The results speak for themselves: an 83% reduction in the fatality risk, and air travel remains one of the most safest modes of transportation in the world. But the point was, it took the FAA collaborating with industry to share information and collaboratively define and assess what is acceptable risk to prevent safety risks before they happen in the first place. So I think we can learn something from this. So what does driving safely mean then, ultimately? So driving safely in this context, I believe, is using societally acceptable values that represent acceptable risk and prove that you are doing so. And so how do machines and humans differ in this regard? Consider a human driver and think about a simple car following scenario. So when you're following another vehicle, what are you told? What do we learn in driver's education? We learn things like the 2-second rule, which in traffic engineering speak we call time headway. And that's where you're following the car in front of you, you note a marker on the road, you count to 2 seconds, and that should be the point at which, or at least greater, that your car should pass the same point. But again, this is an estimate. This is imprecise. It's not scientific. And this is something that's simple for humans to remember and for humans to use while we drive. But with automated vehicles, we have a much better way. We don't have to guess. With automated vehicles, we can calculate this much more precisely. So here's an equation, a kinematic-based equation from the responsibility-sensitive safety model that uses velocity, reaction time, braking capability, acceleration, and all sorts of things to be able to more precisely calculate what would be to make sure that I have enough distance to stop if the vehicle in front of me were to suddenly brake. And so, as I said, that came from this safety model, which is an open and transparent, technology-neutral safety model for autonomous driving. It is flexible. Driving safely is cultural. Driving safely in China is very different than driving safely in the US, just as driving safely in Italy is very different than driving safely in Switzerland. And so the point is, the safety model can be tuned to the level of acceptable risk that is desired in that community. And so it's a very useful framework for regulators to define what is that acceptable balance between safety and usefulness of these vehicles. Here are the 5 rules from RSS, and these should look familiar to any human driver. These are things we are all taught when we learn how to drive. Do not hit someone from behind, that 2-second rule, right? Right of way is something that is given and not taken. Also, that we should be careful in areas with limited visibility. But what does careful mean? What does limited visibility mean? How do I precisely define that for a machine? This is what RSS formalizes, is these informal, implicit rules for safe driving have been formalized into mathematical equations and logical rules that allow us to plug in values that represent what does careful mean. So a very useful tool for us. And so we might ask then, who decides how safe is safe enough? And here's where I think it's important to remember then that not all parameters in these safety models can be measured or known. If we look at the RSS minimum distance calculation, we see that beta max is a parameter that represents an assumption about what is reasonable and foreseeable to expect about the braking capability of the vehicle that I'm following. Because the more aggressive the braking capability of the vehicle that I'm following, the longer the distance I'm going to need to be able to maintain to make sure that I don't crash into that car in front of me if it were to suddenly brake. So what should that value be though? So here's a chart that shows a variety of different values and different braking capabilities for different vehicles on the road. So as you can see, it varies quite significantly. If you're lucky enough to own a new Porsche or Corvette, you have a vehicle that could brake around 12.5 meters per second squared, which happens to be about twice the value that NHTSA research has observed that actual human drivers driving those cars actually perform. So what should we assume? Should we assume what the research says is what's natural and to be expected from other human drivers, 6.56 meters per second squared? Or should we assume the maximum global worst case of some race car somebody has put on the road? If we assume the latter, we're going to have very long following distances that will contribute to worse traffic flow, create congestion, and make everybody annoyed with these super conservative automated vehicles. Assume something more natural, we get a naturalistic drive, we get a comfortable ride, we get an automated vehicle that fits better into the transportation network that we have today, but we have an automated vehicle that cannot guarantee it won't crash into the vehicle it's following if it were to brake with that maximum theoretical braking capability instead of what is reasonable and foreseeable to assume. And so this is why it's so important for us as industry and government together to pick these right values. So what are the role then? So the role of industry is to define these parameters in these safety models and in standards that industry is working on. The role of government is to pick the values. And so we can see you might say that, well, government doesn't do this very often. Well, what about a speed limit? Every time a new road is built, a speed limit is picked. That's a value representing a parameter. So in the US, it's very common to have new roads that are 55 miles per hour. But why 55? Why not 70? Why not 80? Why not 30? Why not 20? If the goal is safety, that value should be 20, because we would significantly reduce the number of fatal accidents if we lowered the speed of these big, heavy metal boxes driving around. But we don't do that, right? We trade off this value between, well, I could choose 20, but then the efficiency of my transportation network is lower. So I pick a higher speed limit knowing that increases the level of risk for more serious injury accidents. And so again, that's that trade-off. Another recent regulation that came from the US recently is minimum sound requirements for electric vehicles. And so this is the case where an electric vehicle is operating at a low speed, and so it needs to emit a sound so that pedestrians like us who are walking around, and this car might be coming from behind, can hear the vehicle, right? Because we've all experienced this probably, right? Where we have an electric vehicle that comes out of nowhere and we didn't hear it coming. And so after much study and deliberation, a new regulation was issued and a value was specified for this parameter, 62 decibels. You'd say, well, why 62? Why not 63? Why not 70? If it was 100 decibels, wouldn't more people hear it? And wouldn't that lead to a safer kind of environment? Yeah, probably. But at some point, it's a balance, right? And so this is another example where industry defined the parameter, which is what level of sound would you like us to produce and at what speeds. Government picked the values. So it's a collaboration between the two for sure, but there are important roles here to understand and to respect. And so is the same then for automated vehicles, that we need government to help us. And we will provide the parameters, we'll provide the data, but at the end of the day, we need to pick some values. What is that maximum assumed braking capability? What is the maximum acceleration we should assume for an occluded pedestrian? Is it the fastest human on the planet, or is it something reasonable? So you get the idea. So at the end of the day, we have this challenge. We need to pick some values for assumptions in order to come up with a definition of what it means to drive safely. But how should government do this? This is a tall task, right? We should respect the complexity and the difficulty in doing this. And again, this is where industry and government can work together. Here is a research study produced by Tongji University in China, a fantastic methodology that was introduced that is one example among many of how would you identify the right values. So they looked at a naturalistic driving data set from Shanghai, almost 20,000 trips over 3 years, and they looked at this data and tried to understand what are the safety critical events. What were the safety critical events that were important, where something was happening that an accident could have been avoided, or an accident was just very narrowly avoided. And they collected all this information and modeled this, and then understood, what if all these human drivers that were experiencing these safety critical events had RSS in their brain? What parameters would they be using, and more specifically, what values would they be using for those parameters that would optimize the prevention of these safety critical events? And then we would then we did an analysis. The Tongji University did this analysis where they used those values to study what percentage coverage for those events did we have, how much better was it compared to humans, to understand, are these the right values, or do we need to adjust them up or down a little bit, making sure that we're continuing to balance a much safer vehicle, but let's not contribute to worse traffic flow or significant congestion just because the automated vehicle is using these values. So a very interesting methodology that, like I said, is one of many, but there are ways to do this. This is not an impossible task, but it's a task that requires collaboration and research to be sure. So at the end of the day, we've shown that RSS provides an open and transparent framework for regulators to define what are these acceptable values that represent a risk balance for things that cannot be known or measured. So where are we now from an industry standpoint? What has the industry been doing? Industry has been quite busy, to be sure, and so let's take a look to understand what they've been doing. So here I'm going to present a hive of activity, if you will, of behavior and standards from industry. So let's break this down into its component parts. So the first thing what we might need to understand is, how did you define, develop, or test the automated vehicle? For that, we need systematic process standards, and we have two excellent standards that are either complete or nearly complete in 26262 and 21448 coming from ISO. Then, okay, so that tells me how I should build something. What about what I should build? Here we have safe by design architectures like ISO 4804 and SAE J3131. But then why do I think what I've built is safe at the end of the day? Well, that's where I might file a safety assessment report with governments, or provide a safety case argumentation compliant with UL 4600. But what I've done then, what do I test? What scenarios are relevant for my testing? And so here's where we need scenarios that will be defined, and there's active work on this. But within each of those scenarios, what constitutes pass or fail? Well, that's why we need metrics. And so we have work that's happening in the Institute for Automated Mobility in Arizona, as well as in the SAE, Validation and Verification Task Force, to understand what are metrics to be used within scenarios that are tested for a vehicle that has a safety case that matches the safe by design architecture and conforms with the systematic process standard. So you get the idea. And then ultimately, how did we do the test? Was it in simulation? Was it on road? What mix of it? How good is my simulator? How good was my on-road test? You know, so we have excellent work happening within the UN that does this as well. So at the end of the day, safety assurance is a framework. And it's important to note that if all I did was follow all of these standards, I have built an automated vehicle in a responsible manner. But I haven't necessarily built one that achieves acceptable risk. And this is ultimately where these assumptions come in, and then the values for those assumptions. And so at the heart of all of this is IEEE 2846, the standard that will help define a framework for understanding acceptable risk. And it's really only if you do all of these things together do we have a complete and comprehensive safety assurance framework for automated vehicles. So in this standard, I am proud to be chairing this standard myself. We have over 25 entities. The standard, called Assumptions for Models and Safety-Related AV Behavior, is one of the first contributions from this working group to collaborate, again, between industry and government to define these assumptions. I'm proud to have Waymo as the vice chair, Uber ATG as the secretary, and we encourage everyone to come join this standard because this is critical work that needs to happen to ultimately lead us to a common definition of what it means for an automated vehicle to drive safely. So let's take a look at a very quick example from our draft standard. We have a simple car following scenario, and so here we are. We have an ego vehicle following another vehicle, as we talked about before. What is an assumption that I need to make ego vehicle in order to not crash in front of that car that I'm following if it were to suddenly brake? And as we already established, this is where we need to assume what is the maximum longitudinal deceleration. But what about a more complex scenario? Here's a scenario that we are working on in the standard that has a pedestrian. Let's say a pedestrian is on the roadway or it's in an urban environment. What do we need to assume about that pedestrian to be able to navigate safely around that pedestrian? We need to assume the pedestrian's maximum speed. What is maximum acceleration? What is their maximum heading angle rate change? All of these things are important kinematic properties about humans that the automated vehicle needs to understand if it wants to have some assurance that it can navigate safely around that pedestrian. And so this is a small example of the work that we're doing in this standard. So in summary, call to action. Industry and government must align on what it means to drive safely. This important work that we're doing in standards is a key place for that to happen, but we need help from the research community as well. We proposed one method here for how we could define or identify the correct values that represent acceptable risk, but certainly there are different methodologies that we could look at as well. So the industry, the research community, and government all working in collaboration can help us solve this challenge on what it means for an automated vehicle to drive safely, to make sure that we have organized and safe introduction of automated vehicles to the industry and to the world. And so we don't have that chaotic future that we could have if we are lacking a common definition of what it means to drive safely. So thank you very much for your time, and I look forward very much to talking with you in the Q&A.